Well, it's Friday, week 5 Friday. We're like halfway through the quarter, kind of, I think. Yes. Well, and it's already the end of October. So next month it's like November, and then as soon as it hits November, it's like, it goes fast because you've got holidays. I guess that's it. But it goes quickly, right? You have a question?
Yeah, I wanted to ask about, with your lectures during the stress, I wanted to ask about the Wednesday for Thanksgiving, but you too.
Oh, yeah. So I won't be teaching Wednesday before Thanksgiving because I'm paid to teach Wednesday before Thanksgiving, and I want to do my job, so I will do my job. And then I do this, and then I give you the quiz answers. So you just watch it sometime. You go eat turkey and go shopping, and then maybe like Sunday night you're like, oh, I got to do that thing. Watch the video, put in your answers. You'll be good. Okay. Or you can like watch it like Wednesday evening or something if it's up there. Okay. Well, happy Halloween, everybody, and I hope you enjoy your candy. And if you are watching on the video, sorry you missed out on the candy, but I hope you have a happy Halloween, or had a happy Halloween, or whatever. Okay. All right. We left off on Wednesday talking about Markov chains. We talked about a Markov chain being ergodic, meaning that it has a stationary distribution, a limiting distribution, and it will reach that if it meets those two criteria of being irreducible, meaning every state communicates with every other state, and it's aperiodic, which at a practical level means one of the states can kind of double back on itself. Okay? One of the states can double back on itself. And then if that's possible, then it becomes aperiodic. Or maybe there's some other structure where you don't have a state that double backs on itself, but you still end up aperiodic. That's also possible. But anyway, if those things are met, then that means there's going to be a limiting distribution, and we designate the limiting distribution. We call that pi. And what we saw on Wednesday was that pi times your transition matrix P goes back to pi, and so pi, that vector of probabilities, that limiting distribution, is the left eigenvector, okay? So here we say multiplying the current distribution at time n, which is denoted by pi n, pi super n means the current distribution at time n by the transition matrix will give you the probability distribution at the next step in time, n plus 1. And that's denoted by pi super n plus 1, okay? So it's a superscript, and it looks like we're raising it to the nth power, but we are not, okay? It just means pi, it's just the notation. Pi at time n, pi super n plus 1, pi at time n plus 1, okay? If you continue multiplying the current distribution by the transition matrix P, it will converge to the stationary distribution if the chain is ergodic, which we talked about. And so here's our transition matrix. 8 to state 0 goes to state 0 and state 1 with probability 0.8 and 0.2. State 1 goes to state 0 and 1 with probabilities 0.6 and 0.4. And when you find the limiting distribution, we find that this has a stationary distribution of 3/4 in state 0 and 1/4 in state 1. And as n goes to infinity, this goes to pi, which is the limiting distribution. And so this is just a demonstration of kind of how the current distribution of states goes about. Okay. Now, a student asked a question after class, and it was a good question, and it was just kind of like, how does this Markov chain thing kind of work, and what does the chain look like? And so, think of kind of a sequence of heads and tails, like flipping a coin. When you flip a coin a bunch of times, the actual values that get produced are things like heads or tails. So you might get heads, heads, tails, 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 heads, heads, tails, heads, tails, heads, heads, something like that, right? And so when you talk about the sequence that gets produced by flipping a coin, or the sequence that gets produced by a Markov chain, it's going to kind of look like a sequence of heads and tails. It's going to just be a bunch of kind of different outcomes. And so when you just look at the outcomes itself, it just looks like it's one of these states. But we can talk about the probability of it landing heads as 0.5, right? We can just talk about what percentage of these outcomes are going to be H, heads, and that's going to be something like 0.5. And we can talk about, what's the probability you get 2 heads in a row and you do 0.5 times 0.5, and you get something like 0.25. But as far as the actual sequence goes, it's going to look like it's just a sequence of outcomes. Okay? And similarly, when we take a sequence of outcomes from this Markov chains, we're just going to see a whole bunch of zeros and ones. It's going to look a lot like flipping a coin, just a little bit, a little bit biased towards producing zeros and ones and something else. Okay? So here, we're going to start off our chain. Our initial setup, we have 100%, we're going to say probability of 1 of being in state 0, and 0 probability of being in state 1. Okay? So, if you start off at state 0, this means you have probability 1 of being in state 0, probability 0 of being in state 1. You multiply it by the transition probability matrix, okay? And then we get 0.8, 0.2, all right? Which says at the second state, you have an 80% probability of still being in state 0, and now you have a 20% probability of being in state 1, okay? And that makes sense because if we started off at state 0, we're going to just look at this top row of probabilities, and we say from state 0, you can go to state 0 with probability 0.8, and state 1 with probability 0.2. So this is where we end up after one iteration. Okay, again, after one iteration, you're either going to be at 0 or 1, but we can just talk about the overall probability that you're in 0. Your overall probability of being in 0 is 0.8. Your overall probability of being in state 1 is 0.2. Okay? And then so we say, well, what's the overall probability of where you're going to be after 2 transitions? Okay? So after 2 transitions, you'll take 0.8, 0.2, multiply it by the transition probability matrix. So you're going to have 0.8 times 0.8, 0.64, plus 0.2 times 0.6, so 0.64 plus 0.12 gives us 0.76. So after 2 iterations, your overall probability of being in state 0 is 0.76. After 2 iterations, your overall probability of being in state 1 is 0.24. Right? Is this okay? This idea of taking your current probability distribution and multiplying it by the transition matrix to get kind of the probability distribution after that transition. So after 3 transitions then, to go from 0.76 and 0.24, you multiply by the transition matrix, your distribution after 3 transitions is 0.752 and 0.248 if you do the multiplication. Okay. And what we start to see is that we can imagine continuing to do this over and over and over again. Right? And so here, I've done basically the same work, but just in R. I'm saying start off with this transition matrix P. We're going to start off with matrix X, which is 1 and 0, 100% in state 0, 0% in state 1. We multiply X by the transition matrix P, store it back into X, and I'm at 0.8, 0.2. X times the transition matrix P again, and I'm at 0.76, 0.24. X times the transition matrix P again, and I'm at 0.752, 0.248. And I can say, hey, let's multiply by the transition probability matrix 1,000 times. Okay? So I apply the transition probability matrix 1,000 times. Each time I take X and multiply it by the matrix P, store it back into X, and I just repeat this 1,000 times. And then where does X end up after 1,000 iterations? It ends up at the stationary distribution. We've converged to the stationary distribution where there's a 75% probability of being in state 0 and a 25% probability of being in state 1. Okay, is that good? It's just kind of like, it's not a proof, but it's just saying, hey, if we just kind of follow this idea of applying the going through a whole bunch of steps in our Markov chain, after say 1,000 iterations, we're going to have a 75% probability of being in state 0 and a 25% probability in state 1. Okay, let me go ahead and give you your first view quiz answer for today. First one is B. B as in bear. B as in bear. Okay, what if we started off in state 1? Okay, so we're going to say 0 probability of being in state 0, 100% probability of being in state 1. Right? So again, the transition probability matrix is for state 1, we say state 1 goes to state 0 with probability of 0.6 and goes to remains at state 1 with probability of 0.4. So after one iteration, we're at 0.6 and 0.4. Okay? And if I do a second transition, so I take this output, 0.6, 0.4, multiply it by the transition probability matrix P, store back it to X, I'm now at 0.72 and 0.28. And if I take this and I multiply it by the transition probability matrix P again, I'm at 0.744 and 0.256. And again, if I keep applying this over and over and over again, say 1,000 times, I end up back at my stationary distribution, 0.75, 0.25, right? And you can start off with any kind of starting distribution, 0, 1, 1, 0, 0.5, 0.5, anything, where at least you have two states that add up to 1, or probabilities that add up to 1. If you apply the transition probability matrix, say 1,000 times or whatever, you're going to end up at the stationary distribution, 0.75, 0.25. Which we said is kind of the left eigenvector, okay? I think a lot of you took 102A with me. Some of you did not, okay? Some of you did not, right? And I think I made you guys do Monopoly, right? I made you guys do Monopoly. And so what we did in Monopoly was you coded up the rules and you had it run for a long time. And then we kept track of like where everybody landed, okay? Now, technically, you could have run a Markov chain, okay? You could have coded all of the transition probabilities as a Markov chain. It would be a big matrix. You have a big transition probability matrix. It's a 40 by 40 matrix, okay? Because there's 40 spaces on the board. And you say, if you say square 0 or square 1, go, you can say, what's the probabilities that I end up, okay? And then you'd say, okay, well, there's a 1 out of 36 probability that you end up in 2 spaces away. There's a 2 out of 36 probability that you end up 3 spaces away. 3 out of 36 probability that you end up 4 spaces away, so on and so forth, okay? And then at one of those probabilities you end up at chance, and then you have to then multiply that by the transition the probabilities that the chance dex sends you to another space on the board, right? So I think chance is 7 spaces away. So you have a 6 out of 36 probability of ending up on chance, and then you have to then multiply it by chance can send you to the railroad with probability, 1 out of 14 cards, can send you to the utility with probability 1 out of 14 cards or something like that. And so you could end up creating the transition probabilities for every step going from one square to another square, okay? And then, once you have that large transition matrix, 40 spaces, 40 by 40, you can find the left eigenvector, and you would find the stationary distribution of this Markov chain, denoted by this big transition probability matrix, and then you get your answer as well, okay? And that's another way to kind of look at the problem of looking at this, right? And I think these are actually, so I think these are people who've approached this monopoly problem from a Markov chain perspective rather than a simulation perspective, okay? All right, so what we said last time was if a Markov chain with transition probability matrix P is ergodic, it will eventually reach its stationary distribution pi. And once it converges from the stationary distribution, then the values that it generates from that point come from the stationary distribution. And today we're going to introduce what's called the metropolis algorithm as a way to design the transition probabilities so that the stationary distribution of the Markov chain is equal to the desired distribution. Because we have some desired distribution that we want to sample from, we're going to design a Markov chain where its transition probabilities will lead to a stationary distribution that matches what we want to target. Now, our first example is going to be very simple. It's a discrete case, okay? And we already know how to generate samples from a discrete distribution, any discrete distribution using inverse CDF method. But we're going to generate values from a discrete distribution using a Markov chain, and we'll use that to then kind of think of how to generate values from other distributions. Okay, so this comes from the textbook Doing Bayesian Data Analysis. It's the textbook with the puppies on it, and I think I got it's linked in the syllabus. I'll put another link on CCLE just so you can find it. It's, again, free as long as you're connected to the UCLA network. All right, and so this is the example, is we're going to imagine a country, a nation, consisting of a chain of islands, okay? And a politician is going to travel from island to island, trying to stay in the public eye. And wants to kind of make sure people can see the politician, and so, but he wants to visit the islands in a way that's proportional to its population. So the island that has a lot of people living on it, he wants to go there frequently. The islands that have very few people living on it, he still wants to go there, but just not as often, okay? And so the way the politician is going to go around deciding, or going around to islands, is he's either going to stay at the end of the day, he says, tomorrow I'm either going to stay at my current island, or I'm going to go to the island to the left, or to the west, or whichever, east, whatever. Okay, he's going to, one way or the other, right? He's going to go either to the island to the west, island to the east, right? So we're going to just imagine the islands are kind of in this line here. And again, we want to visit the islands proportional to their relative population. So he spends most of his time at the dense island, densely populated island, less time at the lowly populated island, okay? And unfortunately, we don't know the total population of the island chain, but that's okay. But we are able to kind of find out the population of the island he's currently on and the population of the adjacent islands. Okay, now you go, well, that's silly. You should just call all the islands up and figure out the total population. True, but we're going to pretend that right now we're just limited to the population of our current island, the population of the island to the left, population of the island to the right, or east and the west. Okay, and so every day the politician will flip a coin. Okay? If the coin lands heads, he's going to propose the island to the west. And if it lands tails, he proposes the island to the east. Right? And what he then does is he's going to check the population of the proposed island and the population of the current island. Okay? If the population of the proposed island is bigger, higher than the current island, he's going to definitely go to the proposed island. And if the population of the proposed island is smaller than the current island, then he goes to the proposed island probabilistically, right? If the probability of moving to that island is going to be the population of the proposed, or the probability of the proposed island divided by the population of the current island. Okay? So if the proposed island has the same population as the current island, that is P proposed divided by P current is equal to 1, he's still going to go there for sure. Okay? If the proposed island is half the size of the current island, he's going to go there with probability 0.5. Okay? And if the proposed island has a population of only 1/10 the current island, he's going to go there only 10% of the time. Okay? And so to kind of do that, he can just pick a random uniform value. If that random uniform value ends up less than this ratio, P move, then he'll move to the proposed island. And if he doesn't move to the proposed island, he stays put at his current island. Okay? And this system, this algorithm, will work. Okay? In the long run, the probability that the politician is on any one of the islands exactly matches the relative population of the island itself. So let's take a look at this example. So let's try this with some real numbers. Okay, so let's say our island chain has 7 islands on it. The islands are numbered from theta equal to 1 in the west and theta equal to 7 in the east. And just for simplicity, the population of each island is proportional to their island number. So island 1 has a population of 1,000, island 2 has a population of 2,000, island 3 has a population of 3,000, island 7 has a population of 7,000. So a total of 28,000 in this nation. And our target distribution, which we want to be our stationary distribution, right? So we want the stationary distribution of our Markov chain to match this distribution so that when we produce values from this Markov chain, it's going to be reflective of basically drawing values from this distribution. So we want to get 1 with probability 1/28, 2 with probability 2/28, 3 with probability 3/28, so on and so forth. This is our desired stationary distribution. Let's say we start off at island 4, which currently has a population of 4,000. We ask, what is the probability the politician will end up at island 5? Okay, next, what's the probability he ends up at island 5? He's starting at island 4. Well, how does he end up at island 5? First, he flips a coin, and then if it lands tails, he's going to propose island 5. So the probability he's going to propose island 5 is 0.5. Because he proposes it if it lands tails. And then if he proposes island 5, he's going to definitely go to island 5 with probability 1, because if we look at the population of island 5, it's 5,000 compared to island 4, which is 4,000. Because island 5 has a bigger population than island 4, we're going to definitely move to that island. That's the kind of the algorithm. The algorithm says if you propose a bigger island, you go to that island. Okay? So the total probability of moving from island 4 to island 5 is going to be 0.5 times 1, or 0.5. So the probability, the transition probability of going from starting at 4 and going to 5, I should say, moving to island 5, if you start off at 4, is 0.5. Okay, what about the other way, right? So if we start off at island 4, what's the probability we end up at island 3? Okay? What's the probability we move to island 3? Well, first we have to propose island 3. That's going to happen with probability 0.5. We flip a coin. If it lands heads, we propose island 3. If we propose island 3, what is the probability we actually go to island 3? Island 3 has a smaller population than island 4. Island 3 has a population of 3,000. Island 4 has a population of 4,000. Or at the stationary distribution, we want to be at island 3 with probability 3/28 versus at the stationary distribution we want to be at island 4 with probability 4/28. So the probability that we will move to island 3 is going to be 3/4. So the total probability of moving from island 4 to island 3 is going to be 0.5. We first have to propose it, multiplied by 3/4. So I end up getting 3/8, 0.375. The total probability of moving to island 3. Okay, therefore, the probability I remain at island 4 is going to be what's left over, which is going to be 1/8. So we're going to say the probability of remaining at island 4 is I either have to propose island 3 and don't go there. So that's going to happen with, I propose island 3 with 0.5 and I don't go there with probability 1/4. Or I propose island 5 and I don't go there. Okay, well, I propose island 5 with probability 0.5, but I always go there, so I never not go there. So that probability is going to be 0. So the total probability I remain at island 4 is 0.125. Okay, and so when I as I'm filling out my transition probability matrix, I can fill out this row, the row for starting off at island 4. The row for starting off at island 4, I have 0.125 probability of remaining at island 4, 0.5 probability of moving to island 5, 0.375 probability of moving to island 3. There's no possibility of ending up at island 2 or 1 or 6 or 7 if I start off at island 4, because I'm only going to move to either the adjacent islands to the east or the west, or I remain put. Okay, so for island 4, the transition probabilities is this. Okay. What about island 1? Okay, if we start off at island 1, what's the probability I end up at island 2? Okay, well, that's going to be the probability of proposing island 2, which is 0.5. And then if I propose island 2, what's the probability I go there? I will go there for sure because island 2 has a bigger population than island 1. So I go there. Total probability I go there is 0.5. Okay, what about, what if I flipped heads? Then I propose the island to the west. Okay, if I'm starting off at island 1, there's no island to the west. I guess we could say we propose island 0. Okay, well, what's the probability we end up at island 0? Well, island 0 does not exist. So we can say, like, that has a population of 0. And so the probability of proposing island 0 is 0.5. The probability I go to island 0, though, is 0. So I will go to island 0 with 0 probability. Which is good. We don't want to go to this non-existent island. All right, which means the probability he stays at island 1 is going to be 0.5. Right? We say, what's the probability we didn't go to island 0? That's 0.5. What's the probability I didn't go to island 2? 0. Total probability I stay at island 1 is 0.5. So the transition probability matrix, as I fill in the next row, looks like this. I've got 0.5, 0.5, and then if I start off at island 1, I can't end up at islands 3, 4, 5, 6, or 7. Okay, and then we can keep kind of filling out the rest of our transition probability matrix. Let's take a look at island 2. Island 2, I have probability 0.5 of going to island 3 for the same reasons of all of the other islands going to the next island. Propose it with probability 0.5. If it's bigger, we go there for sure. All right, what about the probability of going to island 1? First, I have to propose it, which is probability 0.5. And then what's the probability of moving to island 1? We take at the target distribution, that is in the stationary distribution, we want to end up there with probability 1/28. And in the target distribution, we want to end up at island 2, the current island, with probability 2/28. So you take the probabilities from your target probability distribution. Okay, and so when you take this ratio, you get 1/2. So the probability of moving to island 1, if we've proposed it, is 1/2. Therefore, the total probability that we transition from state 2 to state 1 is 0.5 times 0.5, which is 0.25. Okay. So if we start off at state 2, we can go to state 3, we can go to state 1, and the probability that we remain at state 2 has to be everything that's left over. So if this is 0.5, this is 0.25, everything left over is going to be 0.25. Okay? Or you can kind of go through the math. Probability of proposing island 1 and not going to island 1, probability of proposing island 3 and not going to island 3, that's going to add up to 0.25 as well. So, so we have that. Okay? And then we can fill this out. If we start off at island 7, we have a kind of an odd situation. At island 7, island 8 doesn't exist, so we treat it like it has a population of 0. So we're going to move to island 8 with probability 0. What's the probability we go to island 6? Okay? Well, island 6's target probability is 6 28ths. Island 7's target probability is 7/28, so the probability of moving to island 6, if we proposed it, is 6/7. And so the probability of going from island 7 to island 6 is the probability of proposing island 6, which is 0.5, times 6/7, which gives me 3/7. So the total probability I end up at island 6, if I start off at island 7, is 3/7, okay? Which means the probability I remain at island 7 is everything else, which will be 4/7 or 0.5714, okay? Or 8/14, 4/7. There you go. And so if we go through and you fill out the entire transition probability matrix following the rules of this politician's algorithm, this is what you will get, okay? So I think we did island 1, island 2, island 4, and island 7, and then you can verify on your own islands 3, 5, and 6. Okay, but this is going to be kind of the probability that we end up at all of these different locations. Okay, the transition probability matrix. Okay, are there any questions on how any of these numbers may arise? I have it in fraction form and decimal form on the chart here. Second view quiz answer today. Second view quiz answer is the letter E. E as in elephant is your second view quiz answer. Okay, so I took this transition probability matrix, 1/2, 1/2, 1/4, 1/4, 1/2, etc., etc., etc. I filled this out. I built it in R. Okay, I took each of these things. I used rbind to bind these rows into a matrix, single matrix, a 7x7 matrix. Okay? And what we can do is we can find the stationary distribution of this by finding the left eigenvector of the transition probability matrix, okay? Now, the function eigen in R gives us the right eigenvectors. So what we're going to do is we're going to take the eigenvectors of the transpose, right? And that will give me basically the left eigenvector. Well, technically the eigenvector is a vertical vector, but we'll just leave it in row form. Okay, so the row form of the of this will be we can just ask for the eigenvector of the transpose of the transition probability matrix. Okay, so if you take the right eigenvectors of the transpose, that's basically equivalent to the left eigenvectors. Okay, when you take the eigenvectors, they're normalized so that their squared values add up to 1. But what we want is the actual values to add up to 1. So we're going to kind of renormalize this by taking the, we'll take the transition of the right eigenvector. Okay, we're going to take the eigenvector and sum up the values, so we get a total value, and then we're going to just take the values in the eigenvector, divide by the sum, and that way everything will add up to 1. Okay, and this will be our stationary distribution. Okay, the stationary distribution is the left eigenvector. And what do we see? Okay, we have 1/28, 2/28, 3/28, 4/28, 5/28, 6/28, and 7/28. 7/28 is at least a recognizable number of 1/4, 7/28. But everything else also is 1/28, 2/28. It is our target distribution. If you find the eigenvectors, that gives you your target distribution. And just to kind of illustrate that it is indeed your stationary distribution, is that if you take your stationary distribution, which is right here, and you multiply it by the transition probability matrix P, so I do the stationary distribution times the matrix P, we end up getting exactly the same distribution, okay? Indicating that it is indeed the stationary distribution, that after applying the transition probability matrix, we remain with the same distribution. So our distribution remains stationary, and any if this is my distribution right now, after the transition probability matrix, I will end up with the same expected distribution here. Okay? And we can ask, is the stationary distribution equal to our target distribution? Remember, our target distribution is 1/28, 2/28, all the way up to 7/28, and we can just say, hey, is this stationary distribution equal to our target distribution? Indeed, it is. Okay? I say, are they all equal? And it comes back true. So 1/28, 2/28, 3/28, those are all equal to the values that I get. Okay. Is that all right? I created a sequence of plots to kind of illustrate the probabilities that we end up at everywhere, right? So what if we start off at island 4, okay? We're going to say we have a 100% probability of being at island 4, okay? We apply the transition probability matrix. So on the second day, we can end up at island 5 with probability 0.5. We can end up at island 3 with probability 3/8 or 0.375. And I could end up back at island 4 with probability 1/8, 0.125. Okay. After 2 days, I can end up at island 6 with probability 0.25. I can end up at island, these are basically the probability distributions. So that's after 2 days on day 3. On day 4, this is my distribution. And we can keep applying this. So day 5, day 6, day 7, and I could just say, hey, keep taking your current row, multiply it by p, and store it in kind of the next row. And just keep doing this, right? So here it is after 10 days. This is the distribution. After 10 days and 11 days, this is kind of the distribution that we get. Between days 20 and 21, is there much of a difference? So between day 10 and 11, there's a little bit of a difference. Between day 20 and 21, there's a very small difference. And then by the time I do day 99 and day 100, there's hardly any difference between the distributions. We're starting to approach kind of this equilibrium. It's still a detectable difference. It says the mean difference is 3 times 10 to the negative 7. So we haven't reached the true stationary distribution after just 100 iterations, but we're getting pretty close. You know, what's the difference between the distribution on day 99 versus the day 100? It's a very, very small difference, okay? You know, versus day 10 and day 11, there's still a little bit of difference between where we're going to, the probability of ending up at one of these places on day 11 is a little bit different from ending up in places we end up being at day 10. But after applying the transition probability matrix a whole bunch of times, we can see we end up somewhere close to our stationary distribution, okay? And again, there's a few ways you can find it, that stationary distribution. One is you find the left eigenvector of your transition probability matrix. And the other is you can just kind of keep applying that transition probability matrix, you know, say thousands of times, and it will just kind of empirically converge there. Okay, so this is an example of the Metropolis algorithm for a discrete target distribution, okay? And next week, we'll look at applying kind of the same ideas of the Metropolis algorithm, and we'll apply it to a continuous distribution, okay? Not necessarily something discrete like this. But the idea of looking at what this concept back here, of proposing a location and moving to that location based on kind of the target distribution of the proposed location versus the target distribution's value for the current location, that's going to apply. Okay, and that will hold. All right, let me give you your last view quiz answer for today. Last view quiz answer is D. D as in dog. D as in dog. Okay, and that's it. Happy Friday, everybody. Have a happy Halloween. and we will see you guys on Monday.